In this video we will be looking at the components of the fast response action potential. This can be done by plotting membrane potential, changes in membrane potential against time. So we're looking at changes in membrane potential over time. So have a look at the response here. So this response is produced by changes in conductance across the cardiac cell membrane of three principal ions. Firstly is potassium, and sodium, and calcium. And the lines drawn in here are just representing the equilibrium potential of each of these ions. So at rest, cardiac conductive tissue is most highly permeable to potassium ions, so we can say that potassium conductance is high, and there's an outward current of potassium ions which produces the negative resting membrane potential of roughly minus 85 millivolts. This I say roughly because it varies from textbook to textbook depending where you're looking. This resting state is referred to as phase 4 of the cardiac action potential. So when a propagating wave of depolarization reaches the cell, it can potentially depolarize that cell towards up to threshold value of roughly minus 60 millivolts. When this threshold is reached, it activates fast response voltage activated sodium channels. This produces a brief sharp increase in sodium ion conductance, allowing a rapid inward current of sodium ions, depolarizing the cell towards the equilibrium potential of sodium ions. This rapid upstroke is known as phase 0 of the cardiac action potential. Following this, there is a transient outward potassium current, which produces a partial repolarization, and this is phase 1 of the cardiac action potential. Continued repolarization of the cell is offset by the activity of L-type calcium channels. Like the sodium channels responsible for phase 0, these are activated by depolarization to threshold, but they are much slower to activate. So opening of these channels increases calcium conductance, establishing an inward calcium current and producing a plateau in the action potential. This is phase 2 of the cardiac action potential. Repolarization is then completed as the delayed outwardly rectifying potassium channels open, which increase potassium conductance, allowing an outward current of potassium ions again, and therefore repolarizing the cell. Calcium channels are also inactivated at this point, causing a decrease in calcium ion conductance, and shutting off the inward calcium current, and also contributing to repolarization of the cell. So altogether, this response lasts approximately 300 milliseconds. This means that cardiac myocytes are refractory to further impulse generation for quite a significant amount of time. The significance of this long refractory period will be discussed in a bit more detail later on when we come on to talk about antiarrhythmic drugs. So to summarise, we see at rest there is an outward potassium current, and as potassium conductance is high. As we reach threshold, sodium conductance increases very rapidly, and you get an inward sodium current which depolarizes the cell. There is then a transient increase in potassium conductance, so you get a transient outward potassium current again. And then the L-type calcium channels activate, so you get an increase in calcium conductance and an inward calcium current. And then as the delayed rectifier potassium channels activate, again there's an increase in potassium conductance, and the outward potassium current is re-established, returning the cell to the resting membrane potential.